Hello, everyone. It's my honor to have Professor Chris Ruff here, and let me give a short bio of the Professor Chris Ruff. So Chris is a Frederick Bartman Collegiate Professor of Climate and Space Science and Professor of Atmospheric Science and Electric Engineering at University of Michigan in Ann Arbor. He worked previously at Intel Corporation, Hughes Space and Communication, NASA JPL, and Penn State. His research interest is microwave remote sensing methods and technology for Earth science. He is a former editor-in-chief of IEEE transactions on geoscience and remote sensing. He has received numerous NASA and IEEE awards. He's a fellow of IEEE, and he served on the National Academy of Science, Earth Science Decadal Survey panels. He is the principal investigator of the NASA Cyclone Global Navigation Satellite System mission. This mission is the first of its kind, using small satellites to study hurricane surface wind speed and wave surge. So let's welcome Chris and our.
Yeah, thanks, John, and thanks everyone for coming here and having lunch with me. Yeah, I'm going to give you a little bit of background, sort of motivation for the type of science that CYGNSS is trying to do, or was originally designed to do, which has to do with tropical cyclones, which is kind of timely because Michael's going to make landfall here in a couple of hours, I think, in the Florida Panhandle. And actually, that's the reason I was a little bit late here, because I was scrambling with the mission operations people, setting up a bunch of commands to the satellites this morning so that we can turn on a bunch of special high resolution mode when we're going over Florida for the next 4 or 5 days. And I'll show you examples of why we want to do it after landfall here later in the presentation. So yeah, a little motivation for the primary science objectives when we designed the mission, which have to do with tropical cyclones, and then some unexpected results that we've had since we launched, which are related to why we're going to keep taking data for the next week or so in Florida after landfall, some of the things that we can do with the data over land. So, all right, with that, get going here. So, yeah, a little background about some of the people that contributed to the slides that I'm going to be presenting here today. There's a whole bunch of people working on the mission. Some of them are in the room here today, but the slides that I'm using came from some of these folks here. So at the University of Michigan, Darren McCaig's the CalVal lead scientist, and then 2 of my grad students, Raji and David, who are working on high wind retrievals and tropical cyclone parameterization retrievals with our wind data. And the Science Operations Center engineering team is in Ann Arbor doing the data processing and file generation. UCAR in Boulder has a couple of people that are involved in the project. Scott Gleason is the instrument scientist, and Clara Chu is one of the science team members working on hydrologic applications of our land data, and I'll show you some of her results a little later. And then at JPL, Mary Morris was a former grad student of mine, and now she's on the research staff at JPL, and she's also involved with the ocean wind, the tropical cyclone parameterization work. And then Southwest Research Institute in San Antonio built the satellites, and they have a branch in Boulder, which is the Mission Operations Center for CYGNSS, and they sort of drive the satellites. Okay, so the motivation for this project, the mission was measuring winds in tropical cyclones and in the inner core, and these are just a couple of sort of high-level examples of how winds were done before and how they're still done now. So this is a artist's picture of one of the GOES-R, and these are the kind of pictures that you can take with a visible camera in geo, and you can see the eye, and there's techniques like the Dvorak techniques where from the shape and behavior of the cloud tops you can estimate what the intensity of the winds are in the inner core. And this is a way that's, this method is used, especially in the West Pac, in the Western Pacific, where we don't have hurricane hunter planes flying into the storms. This is a common way to estimate the intensity of the storm without actually measuring it, because there's there's correlations between the behavior of the cloud tops and the storm and the strength of the storm. So that's pretty indirect. And then another way is with microwave observations of the winds themselves. And this is, I think this is a picture of trim, just an example. Yeah, and here's some precip images made by, or precip image made by trim. And yeah, this is their precip data product, 3-day precip data product. There's the ITCZ with all that rain and different, rain, organized rain structures here and there. And from the same sensor, TMI, it also measures ocean winds in the microwave by the fractional foam coverage of the water is monotonically related to the wind speed and the emissivity, and that's how you measure wind speed. So here's wind speed in the ocean, and there's two things about this method which limit its utility for applications of tropical cyclones, and in particular applications where you want to measure the wind speed in the inner core. And one of them is the fact that if you look closely, or if you compare these two images, you can see that the places where there's heavy rain, like for example in the ITCZ, are places where the winds are black, and that's because there's a rain flag in the algorithm that says if it's raining, I can't do wind retrievals, and it's because the wavelengths that these sensors operate at are too high, too low. The frequency is too high to be able to penetrate through heavy precip, so you can't see the surface when it's raining hard. So it's not going to work in a inner core of a tropical cyclone. So that's one reason, and then another reason is these are composite images. It says right here, these are 3-day composites, and it's because this is a single satellite, and it has I think about a 1,000-kilometer swath or something. So it takes 3 days of going around before the swath is processed across all the different longitudes to give you a full, global image. And if you have 3-day revisit time, you can't resolve rapidly changing weather like the rapid intensification phase of a storm or something. So that tends to happen over time scales of 24 hours, 12 hours, 36 hours, those sort of time scales for rapid intensification. I mean, Michael's a perfect example of that. It was a Cat 2 a day and a half ago, and it's a Cat 4 right now. So the two sort of driving motivations for the CYGNSS mission design were to be able to penetrate through the heavy precip, to be able to measure the winds in the inner core of the storms, and to be able to get the revisit time down low enough so that we could resolve short time scale processes like rapid intensification. All right. So the way that winds are measured now in hurricanes, sort of like the most famous way to do it, and it's like the backbone of the National Hurricane Center's measurements, is with the SFMR instrument on the NOAA P3s and the Air Force, I think C-130s, I think. And so this is a picture of this instrument. It's a C-band passive microwave instrument. It's got a much longer wavelength, so it can penetrate through the rain and measure surface winds. And they fly on these airplanes, and this is an example of some data. This is old data from flying across, this is Katrina, about a day and a half before landfall. And this is one of the eye wall penetrations by the airplane, and this is the wind speed that it retrieved. Here's one eye wall, the other eye wall, here's the eye, and then you can see these rain bands in the eye wall, and then these are like cutting across these spiral rain bands where the rains are shooting up. So this works, and it can measure winds, and the problem with this is you need to have an airplane there, so you don't get continuous coverage, and you don't generally get any coverage except in the Atlantic when the storms get within 1,000 kilometers or so of the U.S. Right? But anyway, this is the sort of thing that we're trying to do, is measure winds like this from a satellite. Okay, so the CYGNSS mission uses a different kind of microwave remote sensing approach. It's a bistatic radar. There's 8 satellites. The reason for 8 satellites is so that we get the revisit time down low enough. Each satellite has a 4-channel GPS receiver that it's a commercial satellite navigation receiver that's been modified. The back end has an extra coprocessor added to it, so that in addition to doing the standard navigation, it also can process the multipath signal when the GPS signal scatters off the ocean surface and back up into space, we can process that signal and look at how the signal is distorted by the scattering from the ocean surface, and that tells you what the roughness of the surface is, and that tells you what the wind speed is. That's the idea. And again, the driving motivation for this is rapid sampling of ocean winds in the inner core of tropical cyclones. So we got to penetrate through the precip and measure often enough, which we get from 8 satellites. One really nice thing about using GPS as the transmitter half of a radar like this, these bistatic radars, is that the GPS receivers are really mature technology, so they take just a few watts, and there's no transmitter, so we don't have to worry about that. And those two things together allow us to have really small satellites because we don't need to supply a lot of power, and that's the way we managed to get 8 satellites into a relatively small cost cap for the mission. Okay, so the way the remote sensing technique works is bistatic scattering, and we measure the distortion of the GPS signal as it scatters off the ocean surface, back out the roughness from that, and then get the wind from that. And that's the same general principle as traditional backscatter scatterometers, except that it's forward scattering. There's a couple of important differences between the two. One of them, the main one, is with forward scattering, if the ocean's really smooth, you get a really strong specular forward scattered signal, and the rougher it gets, the weaker the specular component of the scattering gets, and more of the scattering is diffuse in other directions. Whereas with backscatter, if the ocean's perfectly smooth, you don't get anything back, and the rougher it is, the stronger the signal is. So there's in the backscatter case, the higher the winds, the stronger the signal, and in the forward scatter case, it's the other way around. The higher the winds, the weaker the signal. Okay, so this is just kind of a cartoon of bistatic scattering. Here's the GPS transmitter. Here's the Cygnus satellite with a little receiver on the bottom. And if the surface were perfectly smooth, there'd be this one unique spot here, which is the specular reflection point, where angle of incidence equals angle of reflection, and the signal will look like it's originating from this point here if you look down at that signal. And this is an example of specular scattering at optical wavelengths, where here's the moon, and here's the reflection of the moon, and the water here on this lake is really, really smooth, so that moon almost looks as sharp as that moon. Okay, so it's, you know, sort of optical quality specular scattering. If the wind blows, the ocean gets, or the water gets rougher, and instead of specular scattering, you get diffuse scattering, and then you get all these little scattering facets here, and the more rough the surface is, the more diffuse the scattering is, and that's the signal that tells you what the wind is. So this is an example of a GPS signal scattering off the ocean surface measured from a satellite. It's one of the first ones ever made. And here's the specular point right here, and then all of this yellow and green stuff is diffuse scattering away from the specular point. And this is the coordinate system here is the Doppler shift of the signal. As you move away from the specular point, there's different Doppler shifts of the signal at different locations, and we have a bank of Doppler filters, and that's how we can sample different places on the ground. And then this coordinate here, CA code chip, this is a GPS jargon. It's basically the range gate of a radar. So we gate the signal in time, so that's this axis, and we gate the signal by Doppler shift. So we have this two-dimensional bank of time delay gates and Doppler shift, Doppler filter banks, and those two things together give you the scattering as a function of delay and Doppler across the ocean. It's called a delay Doppler map of the scattering, and you can map these two coordinates into position, lat long position, to figure out what the scattering is at different places. And so basically you get a two-dimensional image of the diffuse scattering in the vicinity of the specular point. And we make one of these images every second for 4 different GPS signals on the ground that we're tracking at each time with each of 8 satellites, and that's our data product. Okay, so here's an example of what happens to that delay Doppler map, the diffuse scattering at different wind speeds. These are measurements that were made when the specular point was crossing over an NDBC buoy, so we had some ground truth of the wind speed, and you can see the higher the wind is, the weaker the scattering right at the specular point, and the more of the scattering is away from it in diffuse directions, right? And so we make one of these maps, and then from this map we derive the wind speed, okay? sort of see that there's a clear signal here. So the way the wind speed is derived, there's actually a whole bunch of different ways to derive wind speed from those maps, and we use 2 of them in our baseline algorithm, and there's a number of people on the science team working on alternative ways of trying to back the information out. But these are the 2 we use right now. One of them is just the scattering cross sections. So this is very much like the way scatterometers measure wind speed. We just take this box here. This box is about a 15-kilometer box on a side, and we just take the average of the scattering in that box. So it's the average bistatic normalized radar cross-section of the ocean surface within a 15-kilometer area centered on the specular point, and that is inversely proportional to wind speed because the rougher it is, the less scattering there is. So that's one signal. And then another signal is if you take this this delay Doppler map and you integrate out the dependence on Doppler shift, on frequency, you get a one-dimensional function of delay. And that's just like a radar return pulse waveform. With a regular radar, you get a signal back as a function of time. And this is what it looks like. This is the return pulse as a function of time. It's just a one-dimensional integral of the, integrate out the Doppler and look at the dependence on delay. Okay, so it's the radar return waveform, and the slope of that leading edge of the waveform is related to the roughness of the surface. Actually, it's related to the significant wave height, and the steeper the slope is, the smoother the water is. So this way of measuring wind speed is very similar to how traditional radar altimeters measure wind speed by looking at the leading edge slope of the return pulse for an altimeter. So this is sort of like an altimetric approach to wind speed estimation, and this is a scatterometer approach to wind speed estimation, and we use both of them, and then we average them together in this minimum variance way where we take the average of these 2 inversely weighted by their variances, and that's the wind speed that we actually produce. Okay, so yeah, here's some eye candy pictures of the hardware getting built. So here's one of the satellites with its solar arrays opened up, and we're testing the solar arrays. This gives you an idea of how big they are. They're about this big and about 25 kilograms and about 40 watts total power. The science payload is about 10 watts, and then 30 watts is all the rest of the stuff. Here's 4 of the satellites going into a thermal vacuum chamber, and this is a nice picture because this yellow thing right here, that's the receive antenna that's looking down at the ocean surface. It's a 2x3 half-wave microstrip patch antenna with a gain of about 14.5 dBi, and there's 2 of them. There's 2 of them on each satellite, one on this side, another on this side, and they look off to the port and starboard side of the subsatellite ground track, and they're measuring reflected signals. And then there's a small antenna, right here. There's a small antenna on the top, GPS antenna, and that's looking at the direct signal from the GPS coming straight to the antenna, to the satellite, to do both regular GPS navigation and also as a timer, a marker for us to be able to resolve the time delay of the reflected signal and also the Doppler shift, because we need a phase reference for the Doppler shift. So that comes from the direct antenna. Yeah, here it is right here. Here's the direct antenna right here. It's just a little tiny half-wave microstrip patch, and then these bigger antennas get the gain that we need looking down at the surface, because the scattered signal off the surface is a lot weaker than the direct signal. And then this is all 8 of them stacked up all together in the configuration that it's in when we launch, and this is on a big vibration table when we were shaking it to make sure it doesn't break on launch. Okay, and they're all folded up. And yeah, so this is the final integration. This is just a few days before launch. We built this thing. It's a deployment module that all 8 of the satellites hook onto. And these little guys here, these are these little spring-loaded deployment things. They're going to push the satellites out with just the right delta V's relative to each other so that they all get into the orbits that we want. And then this is all 8 of them all connected on. That's the deployment module connected. This is the 3rd stage of the rocket back here. And then this is the fairing that's going to close off the top before we launch. And so it's the whole thing is, they're like 25 kilograms each, and there's 8 of them, and then the deployment module, the total mass is a little less than 300 kilograms. So it's pretty light, even with all 8 satellites. And it was small and light enough that we could use a Pegasus launch vehicle, Pegasus rocket, which is a smaller rocket that can fly. It doesn't need a first stage because it can go on the bottom of this airplane, this L-1011 airplane, and the airplane gets up to about 45,000 feet up in the lower stratosphere, and then it drops the rocket away, and that way you don't need that great big first stage, and it's a lot cheaper. And so our satellites are just this little bit right here. This whole thing is about 65 feet long, I think. Yeah, and I've got a, I don't know if I can, is this thing working here? Okay, yeah, so this is a video that was taken by a chase plane, this small chase plane that was flying underneath the L-1011 with a nice video camera on it to watch it, to make sure that it was partly for safety, to make sure that the thing was, you know, securely on the plane as they ferried out. They took off from Cape Canaveral and went out about an hour east out into the ocean before they dropped it. And the chase plane was there to make sure that it was healthy before they dropped it, and also it was there to take this really.
LC, PLT, copy.
LC PEG, PEG is go for launch.
PLT, LC is go for launch. PLT confirm.
LC, PLT confirms go for launch.
Drop on my mark. 3, 2,
1. Go for release.
Pegasus is away.
And drop. Pegasus is away.
For about 5 seconds so that it gets away from the airplane, and then
Ignition of the Pegasus rocket with Cygnus, helping hurricane forecasters understand and predict the intensity of hurricanes.
About 520 kilometers altitude. And then
Fin actuator system is working properly to control the flight of the vehicle during stage 1.
It coasts for about 3 minutes to make sure that there's no
power buses remain nominal, approximately 30 minutes to 30 seconds.
This is RCO. First motion ignition, first motion time of 13:37:21.
Vehicle is now past max Q. Attitude remains
That's
nominal.
13:37:21.
After this video, this is kind of an artist picture of what happens next. So this is now in low Earth orbit, and the engines have finished, and so all 8 of them are all connected up like this. And this is there's timers that fire these little spring-loaded deployment mechanisms, and that that pushes out the satellites in pairs. Yeah, you can see the antennas, science antennas on the bottom there. And then as soon as they get away from the deployment module, the solar arrays open up, and then the first thing it does is just turn and point at the sun, charge the batteries back up. And then over the course of about 3 weeks, we started talking to all 8 of them the first day, and went through all this engineering commissioning stuff, and then. This was in December 2016, and then a few weeks later we started turning on the GPS system to measure the scattered signals. Okay, so yeah, this is a little bit of detail about this one thing that we did with the mission that, as far as we know, hasn't been done before. And so when we designed the mission, when we were writing the proposal, one of the main driving motivations or guides for how to, what to keep on the system and what to take away from the system was we wanted to have as many satellites as possible, because the more satellites there are, the better the revisit time. And we wanted to be able to sample the rapid intensification phase without any aliasing. So you need to get that sampling down to, under 12 hours, preferably 6 hours, somewhere in that ballpark, to be able to resolve rapid intensification most of the time, anywhere in the tropics. And the way to do that is to have really cheap satellites. And one of the important things to do in the satellite design to keep them really cheap was to not have any propulsion. Okay, so these satellites have no propulsion at all. And what we did was, well, you saw in that picture, they get spit out from they get deployed out with slightly different velocities. There's like this 7 kilometer per second velocity that they all have going forward, the orbit velocity. And then those little tiny kickoffs that we had in slightly different directions, those were of order 1 meter per second. Okay, some of them were about 0.8 meters per second, and some were like 1.2. But it was around 1 meter per second, and then with slightly different directions, right? So we were ejecting. So if you take that 1 meter per second velocity vector, look at the component of it in the direction of the orbital velocity, and you add those 2 vectors together, or those 2 components together, that's the new orbital velocity. So we have the 7 kilometer per second orbital velocity that we can trim to a part in about 1/100% by that tiny extra bit. And so that let us tune exactly what the orbital velocities were of each of the 8 to be slightly different, really, really slightly different, but enough different so that they would slowly drift apart from each other. Okay. And that's what we want. We want them eventually to be spread out all the way around the world, more or less evenly, every 45 degrees around this orbit plane. And so we got them spreading out like that with those slightly different delta V's. And then we needed a way to stop them from spreading apart. And the way to do that is with differential drag, where, you know, if you remember the shape of the satellites, they're pretty two-dimensional. There's this little thing in the middle where all the electronics is, and then there are these great big solar arrays that go out about 160 centimeters by, I think, about 45 centimeters, and they're really thin. So when you're nadir pointed, the solar arrays are like out of the wind. They have minimum drag profile. And if you tilt the satellite up by, I think, 83 degrees of pitch, that maximizes the drag. And the differential drag between the maximum when you're pitched this way and the minimum when you're going edge on is about 6 to 1, the ratio of the drag. And so we change the pitch angle. We have reaction wheels that can change the attitude of the satellite, but no thrust. And we change the relative drag between them, and that's how we can slow one down relative to another to get them all to the same place, get them spaced out. So yeah, it had a huge effect on how many satellites we could afford. And when we originally wrote the proposal, we found it was a series of papers, just, you know, journal articles by there's a couple of research groups, one at MIT and one at McGill in Canada, in the aerospace engineering department of these two schools. And they wrote this series of papers about this idea of using differential drag with no propulsion to get small satellites adjusted and everything. And, you know, there weren't really small satellites back then, or at least not that we knew about. And as far as we knew, it hadn't been done. But they had worked out all the details of how to do this in these papers. So we put that in the proposal and said we're going to do that. And NASA let us try. And it worked pretty well. Actually, there's a couple things about it that didn't work, so we learned a lot about how to do this because it was the first time. But anyway, so this is an example. This is the first time we tried it on orbit. I forget, this was like a week after launch or something. No, sorry, 50 days after launch. This is the first time we tried this. So we're flying along. So this thing here, this is the orbital phase rate. So there's 8 satellites, FM1 through FM8. FM3 is the lowest one. Okay, it was the one with the fastest orbital velocity and so the lowest altitude. And everything else, we just reference everything to that one because the lowest one is the one that, when we do this differential drag thing, you can't go up, you can only go down. And we don't want anybody to go below the lowest one because that'll hurt our lifetime. So we've dragged the higher ones, but we never mess with FM03. That one stays nadir pointed, minimum drag. So this is the number of degrees per day of change in the angular separation between one satellite and the other out of 360 degrees around the orbit plane. So every day, this which FM1 would change 2.62 degrees. It would get 2.62 degrees closer to FM3 each day. And so after whatever 140 or 150 days, that 150 times 2.6 is 360. That's how long it would take to lap. It would go all the way around the Earth one extra time after 250 days or so. Okay. So that's the orbital phase rate. And then right here, we took FM1 and pitched it up 83 degrees to maximize the drag. And this is the data coming from the GPS navigation telling us where it's at. And the phase rate drops, and then we stop pitching after about a day and a half or something, this time here, and then it stabilizes. The phase rate stabilizes at a new rate that's a little bit lower because they're closer in altitude. So the phase rate is more similar because the orbital velocity is more similar. And this slope right here, that was the number we needed to know. Once we know the slope, how quickly we can change the phase rate, then we could do all this planning on figuring out exactly how to make everything be where we want it. So we had an idea what this angle was, or what this, it's actually an acceleration, it's an angular acceleration, just from theory and from these old papers, but we needed to measure it to really be able to do all of our planning. So that was an important day. And these are the derived, the ballistic coefficient of the satellite when you're nadir pointed in high drag, and when you're sun pointed at this intermediate point when you're just charging the batteries and sun pointed. Okay, anyway, so that was a really good thing. And so this is what's happened since launch with our orbits. So on day 1 back here, or this is like day 4, I guess, 4 days after launch, here's the altitude of all 8 satellites. So it's between about 527.5 kilometers and 530 kilometers. That was the range. And the reason they're not all the same, again, is because those delta V's, when we first ejected them out, had slightly different components of velocity in the orbit direction. And that's what changes the orbit velocity and then the altitude. Right? And so, yeah, this is where we started out. And then they're just slowly dropping just because of air friction over time. And then anytime you see the slope change noticeably, like right here, there's a big change in the slope, it's because for this period of time here, this one was put into a high drag mode, so it drops faster. And then, yeah, right here, there's a sustained high drag, so it drops way down. And when it's nadir pointed doing science, this is like the typical, you know, rate of decrease of altitude just from air friction. And this is also pretty close to solar min right here. There's a real strong dependence of this slope here on solar activity, how dense the air is up at 500 kilometers. Later on, if we're still up there in 5 years, these slopes are going to get a little steeper because the air is going to get thicker because of solar activity when you get near solar max. Anyway, this is where we're at right now. So we brought down 5 out of the 8 to the same altitude. So these guys are all sitting at the same altitude. I get these reports are generated daily of where all 8 of them are and how far apart they are from each other in time and space and a bunch of stuff. And these 3 up here are still up there, and we never brought them down. We started bringing this one down, but we brought this one down so that the spacing between these is about the same, and the phase rate between them is about the same. And we're probably not ever going to bring these all the way down. And we thought we'd have all 8 of them down here within less than a year, and we've been up there almost 2 years, and we've gotten 5 out of the 8, but these 3 are still there. And the reasons for it are a little complicated. Well, it's not complicated. It's just unforeseen issues. So one of the things we did, another thing we did, also very important about keep the price of the satellites down so we could have as many as possible to get good sampling, was if you're familiar with electronics that are used on satellites, there's, in general, when you build nice satellites, expensive satellites that have to last for a long time, you use radiation-tolerant electronic parts. If you're familiar with this thing, electronics that are designed to be able to work in the space environment, and they're much more expensive, and also generally not as capable for the same power for processors and things. And but they're used routinely with multi-$100-million satellites, Class B satellites, the really expensive commercial telecom satellites. They all use radiation-tolerant electronics so that they can handle CME things from the sun that have all these little charged particles that mess up the electronics and everything. So that's a normal thing to do with expensive satellites. These satellites anytime you build 8 of something, the first one costs a lot more than the second through the 7th. But the second through the 8th one probably were about $3.5 million each. The first one was maybe $40 million because of all the design work. But $3 million satellite, we couldn't possibly have put radiation-tolerant electronics in there. It would have cost 3 times as much. So there isn't a single radiation-tolerant part in the entire satellite. They're all commercial. They're parts that you could buy, from DigiKey or something. And we did a bunch of screening to make sure that they were reasonably tolerant, but they're not like official NASA or DoD quality radiation-tolerant electronics. And because of that, they get upset all the time. Anytime there's any kind of solar activity, we get single event upsets all the time. There's probably 100 embedded processors scattered around this little satellite doing all these different little things, and they get upsets all the time. And over time, we've come up with a whole bunch of automatic scrubbing routines that go through and look for problems and reset things and reboot things and clean out memory. And it's taken us a long time to figure out how to do this. In the first couple months up there, the satellites were resetting all the time and going into this emergency safe hold mode and pointing at the sun. And then we'd have to figure out what went wrong and reset it and then get it back to doing science. And now it happens once every month or two. That'll happen because we've got a whole bunch of automated systems in place to track all this stuff and automatically recover within tens of seconds and not days of where you have to get people on the ground involved. Anyway, it took a long time to figure that out. And while we were figuring that out, we weren't able to do this. All this stuff that we had these grand plans for getting everything done within 6 months, but it was based on nothing ever going wrong, which is not what happened. So anyway, so now we know. And so we've decided to just leave these where they are for the duration of the mission. And we got them evenly spaced out, which has some nice properties in terms of how often they cross over each other and so on. But to get this one here, to get all the way down to here, we have to put it in high drag mode for about 4 or 5 months. And while it's in high drag mode, you can't do any science, and it's just not worth it because we'd lose all the science data. So we're just going to leave them like this. Okay, but anyway, we learned how to do it with these first 5, so that's a good thing. Okay, this is an animation that shows you how the sampling works. So once the satellites are all evenly spread out, which they are now, or pretty close to it, so here they are every 45 degrees around the orbit plane. These two big ellipses are the antenna patterns of our 2 science antennas. Here's the sub-satellite point here, and then this is one antenna on the starboard side, and then another pattern, one on the port side. These blue ellipses are the specular points of GPS satellites. So usually, at any given time, from if you're up at 500 kilometers altitude, you can usually see around 10 or 11 different GPS satellites up there somewhere at any given time, and each one of them is going to have a specular point someplace on the ground. As soon as one of those specular points enters into our antenna pattern so that we can see it, we acquire it and start doing that processing with the Doppler filters and the time delay and the correlations to generate those delay Doppler maps. So we'll generate delay Doppler maps as long as it's inside of the antenna, okay? And then we just record it and store it, and that's our archive of data. So the winds that we actually measure will be along these stripes. It's like a one-dimensional swath, basically. It's got 1 pixel wide, and then it's as long as the specular point was in the antenna pattern. And if you take all 8 satellites, each one of them has 4 GPS receivers doing this, you get 32 of these points every second. And then if you paste them all together, this is the coverage, the Earth coverage that you get over time. And yeah, you can also see the orbit inclination. We're at a 35-degree orbit inclination, so we spend all our time over the tropics and near tropics where the hurricanes are. Okay, so this is kind of an overview of stuff that's happened. So we got launched in December. We did all of our commissioning and started generating regular regular science data from all 8 satellites in March. We did a bunch of CalVal stuff and then had our first data release to the public at the NASA PODAC. You can go to the PODAC and get all of our data. We started releasing data in May. It was provisional because we hadn't actually validated any of our high wind data. And then I'm sure you guys all remember last summer was really an active Atlantic hurricane season. We had lots of storms and a lot of coordinated work between us and the National Hurricane Center, or the AOC, the people that fly the Hurricane Hunter airplanes. They did a whole bunch, like 25 different coordinated flights where we would tell them exactly when our satellite specular point was going to be going through a particular storm, exactly what time, and the exact heading of the specular point track. And then they would get their plane lined up on that track and fly through the eye wall at the same time as the satellite was going overhead. They did it 25 different times last year. It was really great. We had tons of matchup data. I'll show you some of the matchup data in a couple slides. So we had all that to validate our high wind retrievals. And then shortly after the hurricane season, we had our first non-provisional public release, the 2.0 data, which had validation of the high wind performance in it from these P3 coordinated flights. And then we've been working sort of nonstop since March, really refining our calibration. And we just had a new release last month, 2.1, which cleans up a bunch of details. And what we're working on now is there's a number of people on the science, different groups. There's 4 different groups on the science team that are taking our data and assimilating it into this model. If you're familiar with HWRF, is like the official model used by NOAA, by the HRD, or the National Hurricane Center, for doing forecasts of track and intensity and structure of the storm of hurricanes. And so they've got these science team members have a copy of HWRF, and they're running it and adding in CYGNSS data to the 2017 storms. It's like a reanalysis run to see how much the forecast skill would have been improved if CYGNSS had been used, or how much, in hindsight. And those results are all favorable. There's better skill because you know more about what's going on with the winds in the inner core. And in general, the main reason you want to know the winds in the inner core is the winds are highly correlated with the latent heat flux from the water, evaporating up into the air, and that's the primary energy source for hurricanes. So if you know the winds, you can, parameterize the fluxes going on, not parameterize, measure the fluxes going up into the energy fluxes going up into the storm. So that's the reason why it helps. And there's like, I don't know if any of you are AMS people, but at the AMS annual meeting this January in Phoenix, there's a session, a CYGNSS session that's going to have, I don't know, 6 or 7 different talks specifically about impact on forecast skill of hurricanes from the CYGNSS data, playing back to 2017 data. So there's a lot of stuff going on there with the TC work. And there's also new work going on, which I'm going to show you in a few slides what it looks like. One other thing about making the satellites simple and making the whole system cheap so we could have a lot of them was it was a lot more straightforward to just leave them running all the time. We thought about trying to be clever and just turn them on when we're over the ocean, because that's the ocean science, and that would reduce the amount of data coming down to the ground, which simplifies some things, but it complicates all kinds of mission operations things to do that. So it was simpler overall to just let them run all the time. And it's really good we did, because people started looking at the land data afterwards, after we were up there, and there's a whole bunch of nice stuff about the land data. So now there's a whole new branch of the science team activities looking at the data over land because of that. So we're just going to keep them running like that all the time. And okay, so here's some results. These are matchups. This is for our low wind data. These are matchups between, this is a log density scatter plot between the ground truth wind from ECMWF model and our retrieved wind. And this is the RMS error, or RMS difference between ECMWF and us. And this is the bias in the wind retrievals. This is, I think this is 2.0 data. So these are actually a little better now with the 2.1 release, but pretty similar. And the errors, or the difference, is about 2 meters per second at low winds. The component of this difference due to error in CYGNSS is about 1.4 meters per second. There's a component due to error in ECMWF, and there's a component due to the temporal and spatial decorrelation in the matchups. But most of this error is due to us, due to CYGNSS. And then you can see the error going up as the wind gets higher, and that's a result of what I was talking about earlier about how the scattering cross-section of the ocean surface goes down as the roughness goes up for forward scattering, forward quasi-specular scattering. And so the sensitivity to the wind, d sigma naught d wind speed, that gets smaller as the wind gets higher. And that's the reason why for a given, the amount of noise in our measurements, just, electronic noise, the noise figure of the receiver, that kind of noise, that noise doesn't depend on wind speed. It is what it is in the satellite. But when you're looking at higher wind data up here, the impact of a given amount of noise on your wind retrievals is larger, because d sigma naught d wind speed, the sensitivity of the scattering cross section to wind speed, is weaker at higher wind. And that's what's going on here. So that's just sort of an intrinsic property of this scattering mechanism. Okay, so here's matchup. This is 2.1 data, so this has got some extra improvements in it. But these are some of the Hurricane Hunter coincident overpasses. So CYGNSS is the green line. As we're flying through these different storms, there's a bunch of different storms, Harvey, Jose, Maria, and these are different cuts through by the satellite. This is the wind retrieved from the specular point track, and these are coincident winds by the SFMR instrument, that instrument that I showed you in like one of the earlier slides, the C-band spectrometer on the airplanes, and the agreement is pretty good. Okay, and so this is our sort of master science requirements chart of all the different things that we promised in the proposal and how we're doing relative to them. Here's the uncertainty in low winds, that 1.4 meter per second number. That's the 2.0 meter per second difference, and then you un-RSS the error due to ECMWF and the error due to temporal and spatial correlation, and you get 1.4 meters per second of our error. This is the RMS difference between, the RMS error for CYGNSS at high wind speeds based on those plots I just showed you, the matchups with the Hurricane Hunter, coincident overpasses or eye wall penetrations. So 11% error in wind at high wind, 1.4 meter per second at low wind, and then these other ones. I'm going to go through this. So This is the dynamic range that we were supposed to perform over. This is basically the dynamic range of this matchup data from SFMR. So the SFMR data that I just showed, it goes up to 54 meters per second. So that's how high we validated. And so we need higher wind matchups to get up to 70, which is what we're shooting for. That's like a Cat 5 hurricane. What else? Operation in presence of rain. Yeah, we can't see the rain data at all when we do an eye wall penetration. We've looked really carefully at the scattering cross-section right as it goes through the eye wall where the rain is like 200 millimeters an hour. And you can just barely see this tiny little dip in the signal due to the attenuation. And maybe it's just noise, or maybe it's not some huge dip the way you would see at a higher frequency. So the attenuation or scattering due to the rain is pretty small. Spatial resolution, this is just based on the Doppler and delay filter sizes, the spatial resolution. 100% duty cycle. It was originally 100% duty cycle over the ocean, but we just let it be 100% all the time, which is really good for the land data. The revisit time is 7.5 hours. That's just how often we come back around. The average time it takes to come back around to the same spot, again, anywhere between 38 degrees north latitude and 38 south. That's how often we come back around every spot. This is how much of the Earth we cover every day. Cal-Val work is, the Cal-Val work was necessary to get these errors up here. And then this one here, this is a little bit of a kind of a soft fuzzy requirement that was added on by NASA headquarters to just, nobody really knows exactly what that means. But, we're doing things, we're supporting HRD and NHC. We're supporting the groups that are looking at the impact of forecast skill of adding simulating Cygnus data, and just trying to, we want people to use this data. That's sort of the point of the mission, so that's happening. Okay, so here's some more data. These are overpasses of, these are all Hurricane Maria. Yeah, Hurricane Maria at different times. So what these are is take all the data that happened within a 3-hour window. So these are specular point tracks of the wind happening over different, from different satellites, all aggregated together. And like you can see, some of these have slightly different angles. You can tell they're coming from different satellites. Actually, these are maybe like ascending and descending because they're sloping differently. But anyway, here's the winds. These circles are centered on the National Hurricane Center best track estimate of the storm center is in the middle. And then I think, I don't know if that's the 34-knot wind radius or something. I forget what the radius of this thing is. But anyway, the center is where the best track storm center is. And you can see that, just like there should be, there's higher winds here, and then it falls off. This is one. This is really nice. We found a whole bunch of these with Florence, but we didn't see as many in 2017, where you actually can see the eye, where the wind is really low right in the middle, and then it's higher here, and then it falls off, which is kind of nice. And we saw hardly any of those in 2017, but we're actually seeing a lot of them with Florence, and we haven't gotten the Michael data. Is just getting downlink now from the last couple of days, so we'll go looking for that too and see if we can see it. But with Florence, we had a whole bunch of cuts where there was a dip right when it went through the center, so that was nice. This is old data over Harvey, just before it made landfall. This is like earlier in the day, on the day it made landfall. So this is just 1 hour of data with several different satellites, and the storm center is someplace right around here. This is 1330, and then this is an hour later, 1430, with some other satellites, just to sort of show you what it looks like. So, this is one kind of limitation of this technique, this remote sensing technique, compared to the other ones, is that it's inherently a gappy image. It's not like a cross-track, gap-free image that has, complete dense pixels. There's all these gaps here because the places where we get samples are completely determined by the measurement geometry, and where GPS is and where we are at any given time determines where the specular point is, and those specular points just move across the ocean as we orbit along. And so we got to take what we can get in terms of where we take data and where we don't, right? Okay, so here's some land data, also from Harvey. And so what this is just, well, it's SNR, but it's basically a scaled version of sigma naught. This is the bistatic normalized radar scattering cross-section of land at L-band. This is GPS works at 19-centimeter wavelength, 1575 megahertz. So this is the scattering cross-section at 1575 forward scattering. And this is the day before landfall, and then these are subsequent days after landfall. This is southeast Texas. You know, Houston is right here where that star is. And you can see the red parts spreading out from day to day. And what's going on, it's the flooding. If you remember what happened with Harvey, Harvey made landfall, and then the whole storm just stalled out there and sat there for like 3 or 4 days and dumped whatever, 50, 60 inches of rain on metropolitan Houston. And there was a ton of flooding. And flooded land has way higher scattering, forward scattering cross-sections, like 20 or 30 dB higher. It's huge. And so you get these really strong signals any places where there's flooding. You can see the floodwater spreading out. And if you look at the next 3 or 4 days after this, the red starts to go away again as the floodwaters recede. So that's a nice thing. You can resolve that. And then something else you can resolve, which is sort of a, I mean, flooding is like a limiting case of moist land. So this is trying to look at a soil moisture signal, which there should be a soil moisture signal here, because you know, as land gets wetter, the dielectric constant goes up and the scattering cross section goes up just from, you know, Fresnel reflection, the forward scattering cross section. So this is a soil moisture map derived from SMAP, which is also an L-band instrument on a different satellite. This is a passive instrument with about 35, I think, kilometer resolution. This is the change in soil moisture recorded by SMAP. Yeah, I don't have the time here. I think it's from 1 month to the next. It's like taking a whole month. I think it was like, I forget, it was like March and April or something of 2017. You take 1 month of data, soil moisture, and subtract a month from the previous month. So this is the change in soil moisture month on month, and this is the change in the Cygnus scattering cross section for the same month, and they're obviously correlated. So there's a clear soil moisture signal there. So so there's now a handful of people. So we weren't expecting any of this, and when we first started seeing this data, this is actually Clara Chu at UCAR. She's the first person, as far as I know, who actually started looking at our land data and seeing these signals in it. And I took these maps and a couple of others, these images, to NASA headquarters and showed them this stuff and said, you know, we've got this whole other pile of science we didn't know we could do that's in the data, and there's not a single person funded to look at land data on Cygnus. So they scrambled. This is last summer, and they got a ROSES AO out within like 2 months, and we got 14 investigations selected, like full-blown ROSES investigations for, I don't know, 130, 150K a year for 3 years for 14 people. It was really nice. It came up with a bunch of money, and so now we got a whole bunch of people working on land data for Cygnus because of this. So that's a good thing. This is one of the pictures Clara generated to sort of illustrate the point that we're sensitive to water. So this is a Cygnus image of the Amazon Basin, and you can see all these little tributaries and stuff where there's basically standing water or smooth water that has really strong forward scattering. And if you zoom in on these tributaries, something really nice happens, and I want to preface that with a little explanation of what's going on. So over the ocean, this is the scattering regime that we're almost always in, incoherent scattering. And what's happening is you've got a surface that's much rougher than a wavelength, or the roughness scale size is vertically or comparable to this 19 centimeter wavelength. So you've got your GPS signal here illuminating the surface, and then with incoherent scattering, you just take each one of these little differential facets and let them re-radiate, and you just add up the signals incoherently because they're all so far apart from each other in phase that there's nothing coherent about it. And when you do that, and this is the way the scattering happens over the ocean, and when you work out the sensitivity of the measurement, this is the received power by the Cygnus receiver. The sensitivity of the received power to the ranges involved. There's one range is the distance from here to here, and the other is the distance from here to here, right? It'll go as 1 over r squared propagating down. That's the sort of the energy density incident on the surface. And there's another 1 over r squared because each one of these little facets does 1 over r squared, you know, scattering radiation back up towards us. So that's the sensitivity of ocean scattering signals, and this is consistent with the strength of the signals that we measure on orbit over the ocean. They're proportional to this term. If the surface is a mirror, if the roughness, the vertical roughness scale of the surface is much less than a wavelength, then this is not the right model to use. This is the right model, and you can just use image theory. Just think of a virtual transmitter sitting down here, going up like that, and then the range that matters is the total range from the image source to the receiver, which is this sum here, right? And this is, it gets modulated by the Fresnel reflection coefficient term, but that's like 0.6 or 0.5 or something. But the main difference between this and this is the dependence on range. It's 1 over the square of the sum of the ranges and not this product here. And if you plug in the Cygnus numbers for how far away the GPS is and we are from the ground, the difference between that and that is like 25 dB. It's a gigantic difference. So the coherent one is way bigger. So when you get scattering off of a really smooth surface, the signal strength jumps up by this gigantic amount. So the signal over the land is huge. And because of that, something really nice happens. Okay, so here's a zoom in of this one little tributary in the Amazon River. This is imaged by the SMAP passive microwave imager. So this has got about 30 kilometer-ish resolution. Passive. These are all about the same frequency. This is 1.4 gigahertz, 1.2 gigahertz, and 1.6 gigahertz for Cygnus. This is an image made by the SMAP radar, which worked for a few months and then it broke, I think. But they got, it took some data for a few months. So this is 3 kilometer resolution of the exact same tributary. And then this is the same one imaged by Cygnus. And it's got all these tiny little details here, which are way better than the resolution of this thing. It's actually way better. So 500 meters is, if you're familiar with what's the term? It's the there's this, I forget, it's this communications scattering term for the Fresnel, right? The first Fresnel zone of the scattering. That's what it is. The first Fresnel zone of the scattering is it's this little region right in here that it determines the spatial resolution of a perfectly specular scattered signal. The first Fresnel zone is the range where if you go down, this is the specular point here. If you go down to a slightly different spot and then go back up here and you figure out how far away from the specular point you go before the difference in path length is 90 degrees of wavelength. So 1/4 of 19 centimeters. How far do you have to go out before that happens? That's the first Fresnel zone region of scattering. And that's about 500 meters for our geometry, okay? So the resolution should be 500 meters. That's about what you should be able to see. But that's only true if the coherent smooth surface was actually 500 meters or bigger. If you've got a little tributary here that's only 100 meters or 50 meters across, but its scattering cross-section is 25 dB higher than all the land around it, which it is because of that 1 over R1 plus R2 squared thing, then that tiny little tributary, the scattering from it is going to totally dominate your signal, and you won't hardly even see the land around it, even though it's a lot bigger in area. So we think that's what's going on here. That's why this resolution is ridiculously good. It's certainly a lot better than, this 30 kilometer resolution. That's the typical resolution that we get with Cygnus out over the open ocean, where the resolution is just set by the width of our Doppler filters and range gates and all that kind of regular radar stuff. But with the specular, near coherent or essentially coherent scattering over land with standing water, it's a completely different thing, and the spatial resolution is, this is kind of an open-ended issue here that the science team is kind of wrestling with right now. What is the real spatial resolution of this signal? Because it depends on the scene. Because some of these little tributaries are way less than 500 meters across, and these are really nice pictures. So okay. So I think that's it. All right. So just in summary, we launched in December 2016. All 8 satellites are working fine. They're running all the time, 100% duty cycle, which is really good because of the land data, but also just for capturing things like the rapid intensification that happened yesterday with Michael. We're going to pick it up. We'll pick it up for sure in the data when it gets down. It'll come down in the next day or two. And year 1 results show that we're working fine over tropical cyclones, and we also saw the sensitivity to soil moisture in land and also the ability to image inland flooding when the water is smooth. And now there's sort of moved on to the next stage of the ocean measurements to take our winds and get them into hurricane forecast models and see how it impacts the forecast skill. And they're just starting to ramp up the people on the new people on the science team that are looking at the land data and doing things like developing soil moisture retrieval algorithms, come up with a level 2 data product that's kind of like the SMAP soil moisture product, plus this whole other inland flood inundation thing, which So yeah, like one thing, what I was doing this morning, I was talking with the mission operations people about turning on. We have a bunch of special operations modes the satellite can run in that improve the spatial resolution, because we have a bunch of onboard averaging of the data to keep the data rates down for regularly when you're out over the ocean. But we can turn those off or turn them way down if we want to. It's just the data rate goes up. So we just do it when we're over a target area of interest. So we're doing it right now through Sunday, when the satellites are going over the Florida Panhandle, and that whole region is probably going to get really badly flooded here in the next couple of days. And we'll image the flood inundation and its change in the dry down phase later in the week, hopefully. And yeah, so we were doing this morning is sending the commands up to the satellite so that they'll turn on this high resolution mode when they're over Florida here for the next week or so. And I think that's it. All right, thanks.
Questions?
I had a question about the inland flooding results during Harvey. Does your signal relate to the depth of the water over the land?
It's just the presence of water.
Presence.
Yeah.
It just saturates pretty quickly then, right?
In depth of water at L-band, I don't know what it is. It's millimeters or something, right, for water. Yeah, yeah. So yeah, we can't resolve the depth. It's the presence of water. Yeah. Sorry? Oh, the latency? Yeah, so there's a whole issue with latency. This is like a turf thing. We built into the system the capability to get the latency down to about 3 hours, and we tested it once at the request of NOAA because they wanted to see if we could really get it down that low, and so we ran it last November in this the highest possible rate that we could get the data down. And normally we bring the data down once every other day from each of the 8 satellites. So every day we talk to 4 of them, and the reason for that is the ground network that we use is subcontract. It's a private company. They're headquartered in Philadelphia, and they've got about 20 big dishes scattered around the world, and we rent out time on one in Chile and one in Australia and one in Hawaii. And every contact I sign the invoice, every month. We send them a lot of money, and so it just costs money to bring the data down more often. It's just that simple. And so there's been conversations between people at NOAA, way up the food chain, and people at NASA about this. And my direction from NASA, that's who I work for on this mission, Mike Freilich, he's told me if NOAA wants that low latency data, they can pay for it. Those are his words. So we've demonstrated that we can do it, and we haven't really demonstrated that this is real data to put in an operational forecast model, I think. And until we do that, it wouldn't be reasonable for NOAA to pay for low latency data. I think it's perfectly reasonable. But maybe a year from now, when these new HWRF forecast scale impact studies papers come out, there's a couple of them in review right now, and there's going to be a whole bunch of this stuff presented at the AMS annual. Maybe then they'll decide that it's worth the money. But basically, yeah, our latency is a couple of days right now, and it could be 3 hours.
Yeah, 2 questions. One is, for this CubeSat small side, what's the attitude control accuracy?
Yeah, so these aren't technically CubeSats, right? But they really are. The middle part of the satellite is a 6U CubeSat, and all of the stuff, the power system, the communication system, the attitude control system, all those subsystems were bought from CubeSat companies, small CubeSat companies, and that's where we got the stuff. And the middle part is basically a 6U CubeSat, where all the electronics are and all the spacecraft systems. And the size is actually quite a bit bigger. It's like 27U total, but most of it is hollow. And the only reason it's that big is we needed our antennas to be the size we needed to get the gain we needed to do our science. So it's just some structure to hold the antennas out there, right? So we use CubeSat attitude control systems from Blue Canyon, and the control is about 1/10 of a degree, somewhere in there, 1/10 to 1/4 degree, depending on a bunch of little details, and the knowledge is about 1/10 of that. with the star trackers.
So the altitude control, the accuracy is good enough for you to do the retrieval?
Yeah, so you know one really nice thing about GNSSR, this bistatic radar approach, is the location of the spot on the ground, where you're making your measurements, the specular point location, is completely independent of spacecraft attitude. It's completely independent. The only thing that matters is where's the phase center of that transmit antenna, where's the phase center of our receive antenna. And that uniquely determines the specular point location. And the spacecraft can do this, and that specular point doesn't move at all. So that's the reason why this is so. These are, you know, if you zoom in here, the resolution here is really sharp. And this measurement is not made from one pass. This is from like a month of data aggregated together. And the only way you'd be able to make things this sharp is if the pointing was good to way better, like better than 1/100 of a degree, to keep things resolved that sharply. And the reason that's possible is because it's not dependent on spacecraft attitude. You know, we know exactly where our antenna is and where the GPS antenna is really well. Just the, you know, the location, XYZ location, and that's how we can figure out how to geo-register the scattering signal on the surface. It's got nothing to do with spacecraft attitude. So that's a really nice bonus.
So another question is measurement consistency between the different satellites. Is that exactly same, or you need to do some?
Same is a strong word. Actually, Fauzi's an expert at this because he spent a lot of time comparing different satellites. They should be the same, and this is a really good tool for finding problems. They're supposed to be the same. You know, if you look at, you know, if you filter the data to look at the same spot or the same wind speed at the same measurement geometry, you should get the same scattering cross-section. And if you look at the same class of measurements from different satellites, you get these small differences, and it's because the calibration's not right. And we've used that to back out a whole bunch of second-order things in the calibration to make them be more similar. And yeah, we actually got a little bit worse with 2.1 than with like 2 sandbox runs earlier, and we know why, I think. But anyway, yeah, so the fact that you've got 8 things that are supposed to be seeing the same stuff is a really good tool for validating your calibration and for tuning the calibration algorithms. Yeah, and we try to make them the same. Yeah.
You have a very good resolution on top of Amazon. What about high RFI like zones such as metropolitan areas?
Yeah, so RFI is a very interesting situation. So we have a, I don't know if are you familiar with SMAP at all, or how it deals with RFI? Okay, you know the digital back-end processor that detects and mitigates the RFI? Okay, so I designed that back 10 years ago when I was working on SMAP, and I took that design and put it in Cygnus. So it's got, you know, it's got this kurtosis detector. It's looking at high-order moments of the background noise floor, and when they deviate from Gaussianity, you know that it's man-made, and it's that same thing that SMAP uses. So this has got that same system in it. So we use that to flag the RFI so that it doesn't show up in our science data. You also can make maps of RFI with really low detection thresholds, and we have those as well. And those are very interesting. They vary a lot from week to week, and the parts of the world that have a lot of RFI are often highly correlated with what's going on the front page of the New York Times. Often. Yeah, France. Actually, there's a lot of RFI in Northern Africa, Middle East, a whole bunch of places. Yeah. Yeah. The actual signal strength that's received at our antenna is about 20 dB below our noise floor, negative 20 dB SNR, and we have about 40 dB of processing gain with the incoherent scattering signal, and that's how we get 35 to 40. So we get SNRs of 5 to 20 dB over the ocean because of that processing gain. And then when we're over inland waterways over land with the coherent signal, the processing gain is another 15 dB higher. So we get these super strong signals. But yeah, the actual signal strength. I mean, GPS has got it's a 25-watt transmitter. The GPS, you know, power amplifier, it's got 25 watts, and I forget what it is. It's like 18, 19 dBi gain. It's not a huge antenna, you know. So it's not a huge antenna, and there's not a lot of power. So the actual EIRP is really kind of low for GPS. There's no way we'd be able to pick it up without a lot of processing gain. Yeah. Yep.
So I think that's it. It's thanks.
I'm still gonna be. I'm not going anywhere until dinner time, I guess.
Yeah. Any thoughts, comments about future polar orbiting Cygnus 2?
Yeah. So there's stuff starting to happen. If you're familiar with, I don't know if you've been following what NASA's doing in response to the 2017 Earth Science Decadal. There's a bunch of things happening there, and one of them is this thing called the Designated Observables missions, if you're familiar with that. Yeah, so there are these 4 Designated Observables missions that are called out in the Decadal that NASA is basically following the roadmap that they laid out. And they've assigned mission architecture design teams at Goddard and JPL, and they're starting this month, actually, these design studies, to architect these missions. And there's a number of different, it's actually very similar to, if you're familiar with how they do planetary mission calls, which Earth Science, they've never done it with Earth Science, but for some reason they're going to do the planetary thing with Earth Science now. What they're going to do is headquarters is going to be responsible for the bus. They'll manage the contract with the bus, and they're going to be responsible for the mission operations, the ground operations, and the ground content data networks and all that stuff. And they're going to compete the payloads, the science payloads, which is, I guess that's like a routine thing that planetary missions do all the time, and Earth Science missions has never done that before, so it's a whole new thing. And yeah, so those, the first mission, there's 4 of them, and the first one is supposed to, the architecture studies are starting right now to define them, and the RFPs for the competed payloads are supposed to come out in late 2020. That's the schedule today. I would be surprised if it slips a year, but anyway. So those are happening, and the designated observables, the reason they're called designated observables is because the measurements are specified. The level 2 science data products are specified, and then the competing payload, the people writing these payload proposals will propose hardware that delivers those L2 data products. That's the way it's going to be set up. And there's a whole bunch of, ocean wind, ocean latent heat flux stuff, all that stuff is in there, which is kind of Cygnus related. And there's also a bunch of hydrology stuff in there, which is like land GNSSR related. And those teams are just getting set up now. There was an RFI put out, it was just due like a week and a half ago. Headquarters put out an RFI requesting, non-government participants in these architecture studies, because they've assigned the study leads to specific groups at JPL and Goddard. So that already happened, and about that back in May they worked it out, or they started the process and then they finished it last month. And so this RFI just came out last month asking if anybody else wants to get involved outside of the centers. And I sent one in saying I'd like to get involved if there's any kind of small satellite, constellation, GNSSR, all that kind of stuff. And I haven't heard back from them yet. It was just a week and a half ago I sent it in. So I'm hoping I'll be part of the architecture study for the one that's got, Cygnus-related data products in it. And I'm assuming a whole bunch of people sent in RFIs, so they'll put these mission architecture study teams together and sort of charge ahead for the next 24 months, and then we'll see what we got. That's kind of happening there. Yeah, so we'll see.
Okay,
it'll be competed. It'll be competed. So there's more than one way to measure ocean winds, right? And so there'll be competition to see who's got the best way to do it.
Because from that image, the applications.
There's plenty of other things, but yeah, actually, I don't think ocean winds is going to be it's not going to be the top tier selling point. I think the ocean, you're right. I think what's more likely is the ocean winds will be this nice to have secondary parameter, and this land hydrology stuff will be the thing that sells it. Yeah, I think that's right. Yeah, these pictures are really cool, way cooler than the ones of the ocean winds. Yeah. Although, you know, when you get a little eye right in the middle of that hurricane, those are pretty nice too. So, anyway. Yeah.
Okay, so let's thank Professor Ruff.
Okay,
and if you want to talk to him, you can just stay.
Hey. Oh, thanks. Uh-huh. You know all about the scattering stuff. Is this your bailiwick?
So, going over trees, like in the flooded Amazon, have you seen any of that?
Yeah. So, you know, this stuff it's really pretty new, and there's a bunch of people that, there was a real, you should have been at this meeting, there was a really interesting meeting. The first time we saw this data, we had this meeting at JPL with a whole bunch of scattering people, and like Joel Johnson and Simon Yue got in this really interesting, long, protracted argument about why this looks so nice, and they have different opinions about it. It's not clear why these pictures are so nice.